Hi, I'm Dr. Wellington, but most of my students call me Merlin. Welcome to SWE 100. In this course, we'll be learning how to develop solutions in Java using the tools that engineers use in real life. But before we start, I'd like to introduce a friend of mine.
Hi, I'm Zoomy, and it's my job to keep Merlin in line.
And don't forget me, I'm Jejun, and I already know everything I need to know.
While this course has you practicing programming, the goal is not to make you a programmer. The goal is to make you a software engineer. As an analogy, let's think about the difference between a cook and a chef. A cook needs to know about ingredients and some cooking techniques, but is given a recipe and is told to follow it. That would be a programmer. A programmer is given, here's a solution, will you please write the code for me? But a chef is going to create a whole new culinary experience. To do that, they need to know everything that the cooks know, but they also need to know how to understand how all of the ingredients interact and how different cooking techniques affect the culinary experience. And they need a vision of something that they're going to create that has never been created before. That would be a software engineer. Software engineer needs to know all the things that a programmer needs to know, but needs to be ready to use those tools and techniques to develop software that has never been created before. So how do we become chefs? How do we become software engineers? Well, we're going to have to learn the things programmers learn. So we'll learn about the language and the tools that they use to write code. But we're also going to learn about the tools engineers use to develop language-independent solutions. And we'll learn about some language-independent problem-solving strategies. Then the bottom line is, the only way to learn to be a software engineer is to practice, practice, practice.
Software engineering is a contact sport. You can't learn it by watching people do it. The only way to get better is to do it yourself. Practice, practice, practice.
Part of software engineering is the design of algorithms. An algorithm is a sequential set of steps that will always accomplish a particular task. While nobody else uses this word, we use algorithms all the time. For example, here's an algorithm for starting a car. In order for our algorithm to accomplish its task, it has to be executed by someone or something. Someone or something has to follow those instructions. Our car starting example is useless without a person to execute it. We call the thing that is going to execute the algorithm the target. In order for this to work, we need to think about who or what the target is, and we have to word our algorithm in a language that our target understands. If the person starting the car only speaks Korean, our example algorithm is useless. The target can't understand the instructions, so he can't execute them. Similarly, our algorithm has to be specified at a level of detail appropriate to the target. Think about this instruction. Adjust the mirrors, steering wheel, and your seat. This instruction is fine for an experienced driver, but if the target just got his learning permit, we would probably need much more detail about how to make those adjustments. The target machine for the algorithms we'll write in this class is a computer. Even though it feels like your computer holds games, music, and videos, it really only holds ones and zeros. And that's true for the language that it understands as well. Only ones and zeros. The earlier programmers wrote their instructions in that language, but writing code that the machine will understand is very tedious and error-prone.
Software engineers don't like to do boring, tedious things. Whenever we can, we write a program to make the machine do the tedious part, so we get to do the fun part.
In order to hide the tedious of machine languages from developers, we developed assembly languages. In these languages, we essentially take the machine language and give names to the various commands and their attributes. Then we wrote programs called assemblers to translate that code that the developer wrote into the ones and zeros that the machine understands. The characteristic that lets you know that a language is an assembly language is that every assembly language instruction gets translated into exactly one machine instruction. With assembly languages, the developer writes commands with names we recognize, and then the assembler translates it into the machine code that the target machine can execute. While this is a distinct improvement over the ones and zeros of machine language, assembly code is machine-specific, and coding in assembly language requires intimate knowledge of the instructions the specific target machine understands. This means that code written for an Intel processor for your PC will not run on an ARM processor in your phone. After assembly languages, we developed higher-level languages. By higher level, we mean closer to English and less machine-specific. With higher-level languages, we still need a program to translate our code, called source code, into machine code. These translating programs are called compilers. Compilers are machine-specific because they are translating into a specific machine's language. But the higher-level language is not machine-specific. These are no longer assembly languages because one higher-level instruction may be translated into many machine instructions. So, with higher-level languages, we can write one solution in a higher-level language and use it as input to multiple compilers. This way, one program can be translated to run on two different target machines.
Hold on. Too many details. Let me summarize. Essentially, at this point, there are two kinds of languages we can write code in: assembly languages and high-level languages. The fundamental difference between them is that for assembly languages, one source code instruction translates to one machine instruction. That means the programmer has to know that one machine really well, and that our code will only run on that type of machine. High-level languages are more removed from the hardware. One high-level instruction can translate to many machine instructions. This means that the programmer doesn't need to know as much about a specific kind of hardware. With high-level languages, the compiler is the part of the system that knows the details of the physical machine. This means that we can write our source code once and then run different compilers to translate to the machine code for different types of machines.
That's a great summary, Zumi. High-level languages did make things better. But as the number of types of machines grew, we had new troubles. Higher-level languages helped because one solution could be compiled to run on multiple machines. However, we still have to have a compiler for each type of machine you want your program to run on. In the world of the web, that creates a big problem. When someone comes to your website and wants to run your program, you'd have to figure out which machine she has in order to give her the machine code output by the correct compiler. In fact, even when the hardware is the same, some things, like graphics, can be operating system specific. Making one program run on many different physical machines is still really hard. Java solved the problem of running on many machines by adding one more layer of software, a virtual machine, which gets installed on every physical machine. This piece of software executes a language called Java bytecode by translating it into the language of the machine the virtual machine is running on. So we have machine-specific virtual machines that all understand Java bytecode. Now our compiler can translate our high-level language into one machine language, Java bytecode. That one machine language can be run on every physical machine that has the appropriate virtual machine. This means that we can publish our compiled code on the web without worrying about what kinds of physical machines will run it. All of them can run it.
Wait, that was way too complicated to follow. Try it again.
In Java, we write in high-level language, Java. The compiler translates our solution into a machine language, Java bytecode, where the target machine is a virtual machine, which is just a piece of software. That virtual machine runs the code by translating it into the language of the physical machine it is running on. So, we deploy virtual machines that are physical machine specific, a different virtual machine for your phone than for your desktop. Then we can distribute solutions that have been translated to Java bytecode, and they will run anywhere that has a virtual machine.
I think we better let me take a stab at this one. We write our code in Java. That's the source code. The Java compiler translates that source code into Java bytecode, which is a machine language, but not for a physical machine. It's the machine language of the Java virtual machine. When we want our program to run on one type of physical machine, say for example a PC, we install on that PC the Java virtual machine for that kind of machine, and it runs our Java bytecode for us. Now, suppose we want to run our program on a different kind of machine, say for example a phone. Well, then we install the Java virtual machine for the phone on that physical machine, and our Java bytecode runs on that physical machine too. So the Java virtual machine understands Java bytecode and understands the language of the machine it's running on, and it translates from one to the other. Maybe that's better?
Okay, Zumi, you win on that one. Let me take it from here. In all of this, we've been talking about translating things from one language to another, but that's actually done two different ways. A compiler does the translation once, writes the results to a file, and that file can be used multiple times. This is like translating a book into a new language. With this definition, both compilers and assemblers compile code.
Wouldn't it be nice if we used different words instead of having two meanings for the word compiler?
I agree with you, Zumi. Compiler can mean the specific piece of software that is translating a high-level language into machine code, like the Java compiler compiling into Java bytecode. Or it can mean anything that is making a translation once and saving it so it can be used over and over again. The other strategy for translation is called interpreting. An interpreter translates each instruction when it needs to execute it and throws that translation away after it executes. In other words, it's translating on the fly. This is like a language interpreter for the UN. In the Java world, we use both of these. The compiler translates our source code into Java bytecode once, but the Java virtual machine translates Java bytecode on the fly. It is an interpreter. Truth be told, while we say the Java virtual machine is an interpreter, it precompiles some code and keeps some of its interpreted code around for later use. So it's really a hybrid of an interpreter and a compiler. In this video, we learned about algorithms and how we write them, and how it matters who's going to execute the algorithm, who's the target of that algorithm when we write them. And in order to be able to write good algorithms, we need to understand some types of languages. There are machine languages that are the zeros and ones that the computers understand. There are assembly languages, which are English-ish versions of the instructions the machine understands. But there is still one assembly instruction for each machine instruction. And then there are high-level languages, where the language has become more expressive and a little bit more like English, and they're much more machine independent. In addition, we talked about compilers versus interpreters. And in particular, we talked about how in Java, the machine that is going to be the target of our compiler is a virtual machine, so that we can make code that will run on every kind of physical machine as long as that physical machine has its virtual machine running. Next time, we'll start looking at Java. See you then.
That was a total waste of time. We didn't learn anything about writing any Java at all.
Jejun, you've missed the point. Being a software engineer is about writing good code, not just writing code that works. To write good code, we have to understand how the code is connecting us to the machine.